Okay, so let's get started. Hello, everybody. My name is Ernie Friend, and I'm the director of Flate. And today we have a webinar called "A Universal Programming Approach for Any Make of Programmable Logic Controller" by Dr. Richard Gilbert, and we'll get to that in 1 minute. So, what is Flate? So, Flate drives Florida's world-class manufacturing workforce education and training. And as some of you may know, Florida is a manufacturing state. We're top 10 in the US as far as manufacturing state. There's about 450,000 people working in manufacturing, about 26,000 companies, give or take, in manufacturing. And manufacturing right now is the highest GDP of any other industry in Florida. So manufacturing is a big deal. We have a small but mighty team. Again, my name is Ernie Friend. We've got Dr. Marilyn Barger, the Senior Education Advisor, Daniele Cole, who's a Manager of Career and Technical Education, and Teresa Potter, who is our Community Engagement Manager. So I want to thank them too. Certainly, it takes all of us to make Flate happen, and I definitely appreciate each and every one of them. So the main things that Flate focuses on are career reform and our curriculum reform and development, student pipeline development, and professional development for educators. So as far as student pipeline development, we do that in many ways. One is we promote manufacturing education across the state. We do a lot of manufacturing month events. We've got a manufacturing dashboard that if you're not familiar with, you can go to the flate.org website and take a look at that. We also host the Manufacturing Educator Awards, which we just announced the winners. You should be seeing some information coming on that soon. But if you want to look about the awards, again, you can go to the flate.org website. Teresa does a great job of publishing a monthly newsletter. We also support STEM summer camps, and we develop and disseminate resources for recruiting girls and trying to get more people interested in manufacturing as a career. Professional development for educators. We've got something called the Forum for Engineering Technology Education, the ET Forum. Hopefully a lot of you have attended that if you're educators. That is it's for all the state colleges anyway that around the state that have manufacturing programs. We hosted in different schools around the state. The last one about a month ago was at the State College of Florida. The one coming up at the end of September 26th and 27th, I believe, will be hosted at Palm Beach State College. We also host educator workshops. We do those throughout the year, as well as in the summer. We attend conferences to support, or we have conference attendance to support for faculty. We do online webinars, which is an example today, and we also do program mentoring. So if you're, if you need assistance with, connecting with industry or growing your program, those kind of things, certainly you can contact us and we'll do our best to help you. Flate has several resources that you can use. There's lots and lots of content there that's very useful. As a matter of fact, one of the webinars that we did, that Teresa and Daniele did, was about these resources and what's in there for manufacturing month. So we got the flate.org website, Made in Florida, and a wiki with some really, really good resources that you could use working with students. Okay, now it's my pleasure to introduce Dr. Richard Gilbert, a professor and researcher from the University of South Florida, and he's going to talk to us today about a universal programming approach for any make of programmable logic controller, or PLC. It's all yours, Dr. Gilbert.
Okay, thank you very much. Here is the table of content for today's webinar, presented visually in a slightly different format, but we'll just go from the top down. And the first item is to overview for the challenge that we face. we need and we can use a universal program approach that can be used with any PLC. So there's the UBetchem PLC, and we can send that to you in the mail pretty cheaply. And it represents any programmable logic controller made by anybody. Now, here's some real ones. Not that the UBetchem one wasn't real, but you might want to buy these first. And there's a collection in one visual grouping. And now what's going on? There is on the left side, the real world, which is the PLC, but mainly its input-output ports, which are over on the right side of it. And I don't know if you can, I don't know this. Can you see me moving my little arrow? Okay, good. So the over here, but the interesting thing is the programmable controller doesn't have any actual connection to the real world items. The PLC works in a virtual world. Right? It's completely intangible. It's a virtual world. And the best way for us to understand how to really make any PLC work is to understand that you can't use the verbal terminology. You can, but if you use the verbiage I'm trying to present today, you will be able to do a lot more programming with a lot more machines. So avoid using specific PLC manufacturing labels and icons. Here's an example of a PLC single rung program. Here's a different example. The message is different. Well, actually, the message is the same, but the way it's done is different. Right? What's going on is that there are buttons and sensors that change as time goes on. The technician gets that information by looking at the input register of the PLC. You may not be able to predict what's going to happen inside the PLC, but there's always going to be an input register. The PLC, on the other side, doesn't care about anything at all because it works out of information that it stores in its own memory locations. So the PLC world, there's a tangible and the virtual. In the tangible side, the program is designed, it's constructed, and it's inserted into the PLC any way that people do it. The program is completely controlled by the author or authors before it's executed by the PLC. Once you give your program to the PLC, you can kiss that program goodbye, because in the virtual world of the PLC, the program authors have no control of the inputs, no control of the outputs, no further influence on the program, because the programmable controller rewrites the author's program every cycle of the program's life. So the challenge is to use a vocabulary that will put that shaded idea into play without using a particular manufacturer's definition of an icon, because that only belongs to the manufacturer. All right, so in summary, the icons are used in programs, and the program executes the icons inside its own world. There are standard symbols that are used to get the idea across. The ANSI standards are a good example. People like to use those, right? They're in the real world. They have a specific meaning, and each symbol only has one meaning. In the virtual world inside the PLC, every single symbol has no meaning or a whole bunch of meanings, as you wish. So only in the real world do you get one-on-one visual assignment. And in the virtual world, it depends on what happens between the interface, which is the I/O devices. So we need a language that approaches the work effectively for any PLC program. All right, now let's take a quick look at the end game. We're going to work on this particular industry problem. And I'm bringing it up right now because there is a diagram that is the schematic ladder diagram that I believe you have access to in already. Notice something here, a little bit of history. These things have been called schematic ladder diagrams forever, before there was such a thing as a programmable controller. So the first people who started doing programmable controlling called their program language entity a ladder diagram. So make sure you understand virtual and real. This is a real diagram. Used to be on a piece of paper. Nowadays it's in a computer format, and it represents real symbols. All right, here we go. Let's take a look at the vocabulary that you need. And you need it, if it isn't already in your repertoire, start using it. It's simple vocabulary. There are situations in your life. There are situations in everybody's life. It's best focused on 2 words for those situations, active and passive. That's when you can do that. For example, here's a firebox. There's no fire alarm going. The box is just sitting there on the wall. Is it active or passive? It is, in fact, passive. It has a job to do, but it's not doing it right now. Right? There is a fire. All right. Somebody has pulled or is pulling the lever on the box. Is the red box active or passive? Well, I just gave you the passive situation. This better be the active situation. All right, another quick, simple example. Here's a red light, a turn lane red light, by the way, and a vehicle. Is the automobile active or passive? It depends on the perspective. Let's take a look at the 2 perspectives available. There is the traffic lights view. Right now, he's a friendly little guy. He's got a job, and right now he's very active. He expects everybody that's staring at him to stop. Not the light on the right. The light on the right is green, right? But over here on the left, from this perspective of this guy, he's got a very important mission, which is everybody stop. What about the automobile? The automobile is, in fact, in its passive mode. So you're getting the sense these words are fluid, active and passive. They depend on what's going on. Why is the car passive? Because its job in life is to move along and take us to the nearest Starbucks. This case, that's not happening, so the car is waiting to go active. Got the general gist here? It's not hard, right? So there are situations, the verbiage is active and passive. You look at the situation, you make a decision. Now there are devices, there are things. Those things are either active high things or active low things. So when the thing is active inside the computer world, it's associated with the logic 1, and when things are active low, it's associated with the logic 0. Likewise, there are signals. So this is the information being sent by the device. And choices are high and low, right? And the positive logic assignment is high means logic 1. So the verbiage is active and passive for situations, active high, active low for devices, high and low for signals. Don't confuse them, and don't let your students confuse them. And you should mildly correct them if they say them incorrectly. They have to have a habit here of doing this without thinking. All right, let's take a look at continuity, another big deal word that we don't use enough to facilitate how to program. Notice I haven't even started a program yet. Okay, continuity. This is pretty straightforward. All you really do, I would have said, I like to say fickle finger of fate, but I won't do that. The idea is, can you get your mind's eye finger from the left side of the drawing all the way over to the right side? Remember, the PLC will rewrite your program after you give it to them, and you have no more say. The continuity depends on the content of the input registers, and we'll work on that more in detail. And the PLC generates its actions when the ladder program code is continued. That is, something exciting happens when you can get your finger all the way over to this side. All right, so here is a straightforward program idea. You have it on a piece of paper. Does it reflect a continuous or non-continuous idea? Well, the first thing is you have to live with the people that you live with. And one of the groups you live with is the OSHA group and other versions of it. And it is, at least in the United States, almost a requirement that every time you have a stop button, it has to be an active low device. So that's why we went through that vocabulary just minutes ago. So in this webinar, the safety requirement makes the stop button an active low device. Companies get to choose universally what they want for a start button. Most of them like them to be active high buttons, and any other sensors in there depend on a bunch of parameters that may or not be set by company policy. Okay, so that's what the question mark there is implying. This is the human view, right? The human view is of interest to you when you haven't given the idea to the computer, the PLC. And the PLC is a computer, right? But this does reflect something. 99% of the time, the stop button is passive. 99% of the time, the start button is passive. 99% of the time, the level sensor is active. This should make sense. Remember, we're trying to fill something. If we're not filling anything at all, and it's just sitting idle, not working, so the stop button is passive, and the start button is passive. Once you start pushing buttons, then they go active. The level sensor is always active but it may not have any say about what's going on. So that's why I assign those percentages. All well and good, but the big message here is don't pay so much attention to the part that I've covered up in blue. What really matters is what's inside the programmable controller. And the first thing inside the programmable controller is the input module. So here's a situation where we have a start button, a level sensor, and a stop button. This is the general information from the human being. We want to know if it's continuous. The information that really matters is over here that the PLC has collected from its input module. And they're all question marks here because we're just getting started with what's going on. Take a look at the input module. For this particular example in this webinar, notice there's an X. That X means it doesn't matter what that information is there. Why does it not matter? Because if you look at the input port, there's no wire connected to it. What's the message here? For everyone, you connect not this drawing primarily, but what's on the input port and what the register says. All right. So how does you make this work? You always follow the moose. I always follow the moose, been following it since he showed up. And over here is the simple thing in this idea, so we can follow the moose easily. All we're doing is filling up a tank, and this is the level sensor that's bobbing up or down, depending on whether fluid is coming or going. Right. We're going to look at 4 scenarios for this situation. What's the situation? We've got a tank that sometimes has to be filled with water or fluid. So here are those situation scenarios in bigger print. Overnight, there's nothing going on. There's nobody in the plant. There's nobody pushing buttons. That's scenario 0. Scenario number 1 is an operator comes in first thing in the morning and holds a button in, right? Now, the buttons are actually called momentaries, but most people just say they're start push buttons. The second scenario, and we're breaking this down into small pieces. The first scenario is what happens when the operator holds the button in. The second scenario is what happens when the button is released. And then another scenario is what happens when the stop button is depressed. And then finally, what happens when you fill the tank. So those are the scenarios for this situation. All right, so situation number 0, what was that one? Overnight, nobody's there. This information over here is interesting. There's our moose wondering about continuity, right? But here's the information that matters, right? The stop sees a 1. This is the middle of the night. Nobody's pushing the stop button. The stop button is passive. There's a logic 1 signal showing up in the input register. The level is a logic 1. Now, down here, here it is. The tank was empty at the end of the shift, so there's no fluid in the tank. So the level alarm is active, right? Because it's putting out a 1 signal that's in the register. Doesn't matter what's on X, and nobody's pushing the start button. So what's the visual message? Notice the active low stop button is sending a 1 to the PLC. The active high start button is sending a 0 to the PLC. The level sense low is an active high device because there's no fluid in the tank, which you can look at as a technician or an engineer. And if you look at the PLC, it says 1. All right, so that's scenario number 0. Human perspective, the computer's perspective. So Bullwinkle can get that far. He can't get any further. There's no continuity. Continuity is he has to get all the way over past the circle that says tank pump from the human's perspective. But you should have seen that right here from the get-go, because the stop button isn't getting in his way. The level sensor isn't getting in his way, but the start concept isn't letting it happen because nobody's pushing the button. This is really straightforward stuff, and any student can understand it if it's repeated and always using the same language. So scenario number 1, operator has pushed the button. There is continuity. The moose has gone all the way to the right. Right? He went right straight across this horizontal line. That message is also, I see it in this input register information. The quicker everyone can see this human diagram, this story, and the moose, just by looking at this information, the more effective this technique is going to be. Okay, that's number 1. Let's see what's going to happen next. All right, so that's the idea for an application. Let's take a look at the continuity concept, which I think we just did, but if we did, it's going to just come to right where we are, and I can just go right back. And now we'll do some scenarios. So we did scenario 0 and scenario number 1. Scenario number 2, remember it was 8 o'clock in the morning. The technician, the operator, not the technician, the operator is holding the button in. Scenario number 2 is he lets go or she lets go of the button. Scenario number 3 will come to as we go along. Okay, so scenario number 2. So look what happened here. Hopefully you remember that before, when the button is depressed, this was a 1. Right? That allowed us to get all the way over to here. Right? Somehow this path became available. Right? And we haven't talked about how to do this yet, but it becomes available. And there's still continuity all the way over to the other side. So what's this mean? We don't have to hire somebody to lean on the start button all day. It can be released, and the Programmable Logic Controller will remember that, and the path now goes this way. So that was scenario number 2. All of that pictures was fine and dandy, but we need to get out of the picture world and get into the PLC's mindset. There is information available coming from the input module. It is transferred out of the real world into the virtual world, into the PLC module register. You have no say about how this is arranged. I've just made it visually sort of easier for you to see. The PLC reads this register once every time it completely goes through the whole program. And we'll come back to that idea and why that's terribly important. So here is an author envisioned situation that has 4 scenarios, something to do with the start, something to do with level, something to do with stop, something to do with pumping fluid. Here is the input information in this green register, and it has to go through the real world barrier into the virtual world, same information. That information is processed by the PLC, transferred to a register inside the PLC and moved back out to the real world to the output module. So here's status number situation scenario status number 3. Let's see what we can do. Here's the information. Remember, the X means don't worry about it. It doesn't mean anything to this story. The stop, active or passive? Hopefully it's popping in. The stop is active now. There's a 0 there. The signal is the low. What does that tell you? It has to tell you that this concept here, this stop idea, which is an active low button, must be active. That's why there's a low. So what does that mean? It means that there's a stop there. Somebody has pushed the stop button there. It's holding the stop button in at least. So that comes over here. Notice that the level is still interested in having fluid be put in. It's an active high device. Nobody's playing with the start button. The programmable controller stews about this, and it sends this information back out, which hopefully really makes good sense. There's no motors running. There's no LED status indicators. Why? Because somebody has pushed the stop. The idea here is to fill a tank. All right, so here is the output module. The assignments here are associated with the locations in the register. All right, the stop button is active. Repeat what I said because it's important. All right, and over here I show you the input and the output registers. Again, PLC reads and writes the memory registers just once per program cycle. All right, status number 4. I don't remember what it is, but maybe you do, but I don't have to worry about it because it's right here. This status number 4. And what is it? The stop button is active or passive? Hopefully you're popping right in with passive. The start button is active or passive? Hopefully you're popping right in your brain with passive. The level is active or passive? Hopefully you appreciate that it's passive. So this information tells you what about this pump program and pumping process. It's over. It's not doing anything. So that was it finished its job, and we're proud of it. Okay, so the low-level sensor, just to remind you, was an active high device. It's now sending a low signal in. That's the only really new idea here. All right. Okay, so what's going on? This is to remind me to tell you that there's always an e-stop, an emergency stop, and it will not be part of the code that we're going to develop for the application, but it has to be in the programmable controller. What is in the application is a start button, a stop button, and the level sensor. So you get continuity depending on what's happening, what the question mark fill-ins are. All right, let's take a quick look at some scenarios. All right, we did this already, scenario 2, 3, and 4. So we'll go back. Let's look at troubleshooting. This is a quick idea. All right, so this is a new situation. You've been called in, everything's been running, and the tank is overflowing. All right, so the technician and the floor engineer, their feet are getting wet and their socks are going to get wet pretty soon if they don't do something about this. Is it the programmable controller's fault? Now, fault is a bad word, but is the problem being generated by the programmable controller? All right. So let's take a bigger look. So the answer is right there staring us in the face. And I'm going to go quiet to give you a chance to either comment or make sure you do or don't know whether it's the PLC's problem. Staring at this, it's sequential. The first thing that is important is the green register in the outside world. That's what the programmable input module sees, this nibble. It gets transferred inside the PLC, and the PLC thought about this and put out this conclusion and sent that information to the output module. So, is the PLC the source of the problem? No. How's that for being forceful? And the longer you stare at the programmable controller and the longer you try to fix the problem with the programmable controller, deeper and deeper you're going to be in water. All right, so before your head goes underwater, why did I say no so forcefully? Well, going backwards, the previous slides, motor 3 was the player. And what is the information about motor 3? Is it an active high or an active low device? It's active low, right? How do I know that? Well, I looked at the I/O port maybe earlier, but it's also when we programmed this thing, we made sure the label had a line over it, right? So this whole image, motor 3 with a line over it, means motor 3 is an active low device. Maybe I don't know how to wire it that way, but that's the way it is. And what's the signal being sent to the motor? A logic 1. So as far as the programmable controller is concerned, what's going on? Nothing. And it sent the information to do what with the pump? Turn it off. But what is happening? You're up to your waist now in water, by the way, because you haven't moved away from the control panel to go, where should you be swimming to? You should be heading to where the pump is, because what's going on there? There's something electrically or physically wrong with that pump part of it. Everybody sort of see where we go with this? Okay, so that's an easy troubleshooting situation. All of this requires you to be able to count. Now, I know you think this is silly, or you might think because you already know how to count, but let's go through this. It's about 2 minutes. I don't have to say too much about this. How do you count? It depends on what you're counting. Please notice the count on the right-hand side showing up, and the person responsible for the count, of course. All right, so that was a straightforward example. It's a base 2 numbering system. It's counting in base 2. How many digits did it use? 2, a 0 and a 1. What digit never showed up? The digit 2. It shouldn't take a student terribly long to memorize that characteristic and now know how to count. And it's universally that way. So let's try one more. There's a box. There's nothing in it. We're going to count in base 4. So we filled up one box already. Now we filled up the second box, or we're working on the third box. Okay, look at the count. Right, and we're in the process now of filling up another box, and we just filled up another box, and look at the count. This is a base 4 counting process. You see the digits? 0, 1, 2, 3. What digit isn't there? 4. Straightforward stuff, but important. So now we know how to count. So now I'll spend the rest of my time with you on the actual example. And Teresa, I don't know what the end game time is you need, but if I get close to it, just yell at me. So the application is a biotech firm where they're making protein recipes, and they can't afford to have the power drop because there's a large scale process. There's a lot of pumps going on. It's a complicated series of pumps. They can't afford to have even small blips because they have to start it over. Currently, they're starting everything over by hand, which could cause a problem with their own power supply. So they need a fix to this problem, which is some way to automatically start getting the human being out of being the person responsible for pushing the restarts. All right, here's our schematic ladder diagram again, which you also have a copy of, but it'll be up here long enough and you'll get familiar with it as we go along. This is what the team wants to happen inside the plant, and we want a programmable controller to do it. So here is a procedure that I recommend. The first thing you do is assign devices to the addresses, determine what this means, and then determine if the input devices and output devices are active and high or active low. Notice you should avoid FFC, FFS, right? And that's failure to follow the steps. What's probably going to happen if you do that? All right, now that was not Dorothy, right? That was Alice. Dorothy took a trip and went someplace that people could help. If Alice takes that trip, there's nobody there to help except a vicious cat. So you don't want to do that unless you have to. The first step is to assign the addresses. The second step is to work out what they mean. So we'll go through that as we go along. So now we're looking at address assignment. And the addresses have been assigned. There is a stop idea, there's a start idea, there is a timeout idea, and there is a level full idea, which is not implicit here, by the way, because what's the sense of filling something if it doesn't get full? So you need a sensor for that. They're right across here. These registers here are additional registers that are inside the PLC. I just didn't show you the green one or the red one. All right, so we're going to assign, here's the input port. Notice that the stop push button is at a bit address. It's at a port address. And what's that port address could be 0 or 1, depending on the PLC you're using. For the one that I'm using, that's the Ubetchums, it's port number 0. So this is port 0, this is port 1, port 2, and port 3. Port 0, port 1, port 2, port 3. So there's port 0, the stop is 0, port 0, port 3, port 3, 2. Notice there's something else going on here. I did it this way so you could see the labeling of stop and start. They're at extremes. One's at the right-hand side, and the other's on the left. That's a very common practice done to cut down the possibility of the technician who has to do something with the wire associated with the stop not accidentally doing it with the start. It could still happen, but at least it's not right next to it. All right, so what else is going on here? There is the bit address, but there's also the register address. And so now I've added the input register and the output register. I've highlighted them as green and red, put them on with all the rest of them. And there they are. This is register 5301 all the way down to 5307. All right, now it's time to make you think for a second. Please write it down, scribble it down so you know that you are not kidding yourself. What's the next register's address right here? Right. Make sure, say it 4 times so you at least can remember that you did it right correctly, or you need to think about it. So here we go. Are we ready? I think it's going to show up right now. 5310. So what's the hidden information here? Notice the count is smiling. because the count expected what? You should have recognized way from the very beginning when you had to stare at the programmable controller. You have to find out what base it likes to count in. This one likes to count in base 8. Why do I know it's base 8? Because the last number digit was a 7. And we went to the next significant figure was 5310. It turns out in the vernacular, and you have to be careful until everybody's really comfortable and knows you do this, because when I'm working with people that already understand it, I just say the address is 5310, because they get it. But I would not do that in a classroom or with new technicians. Okay, so I am going to break the rule and jump to determine the process. So I'm going to jump to what this means. There's our friend warning us about it, but this is so straightforward, I wanted to get it out of the way. The intent of this document, the schematic, is that the process on demand fills and mixes a batch with time constraints as assigned. It's that simple. And this is when the team was using the ladder schematic diagram symbols, the ANSI choices. All right, so there's our friend, the input port. We're moving on to the next step, which was after determine they're active or passive. There are all the inputs. It's labeled. There's reason you could see that easily with the PLC. So the stop is active low, start, fill, and things are active high. And there's the register again. All right. Now, the intent is important here. The diagram you started with was written with symbols available that are one-time use only, but not necessarily the ones you'll use in your program. The big deal here is that the stop button, even though it's shown in the language in the schematic ladder diagram, is normally closed. That's fine for the intent, right? But we have to adjust to the actual reality. Here's a cartoon, right? Notice that there is continuity from this line over to here, right? It's a high signal because the continuity can go like that. Bullwinkle's quite pleased to walk across to the next point. Here it is in bigger print. There's continuity from the voltage signal source right to the high signal. When you depress the button, right, that continuity goes away and Bullwinkle fades into the sunset. What about signals? Remember, there are a whole bunch of signals. The easiest one's the voltage. Here is the cartoon of this situation, right? The voltage comes from here, is continuous over here. You can look at it here, and it continues to go to there. The voltage right there is 1/2 that voltage. Here, the voltage here is 0. I'm putting this in front of you. Don't let anybody tell you they don't understand circuits. They can't work this out. There's no circuit here. That red resistor is the same value as that one. So the voltage to go all the way around here uses all the voltage, so half of it must be gone. Right? Circuits are not important when it comes to actually working with the PLC, the input and output zone. All right, so that's where this, don't worry about the fact that this had to be changed. So let's work from left to right with the symbols we haven't taken care of. We've taken care of stop, start. The timeout is a signal coming from an input into the PLC. This thing called TR1, this symbol, right, has a meaning, right? The phrases people like to use are energize and de-energize. Energize will, when the charge flow is flowing, it immediately generates a magnetic field around the coil. De-energize means that when charge stops flowing on the relay coil, the magnetic field goes away. So this symbol is for a normally open, right? And the magnetic field will pull the contacts closed. So contact the set opens for 5 seconds after the magnetic field disappears. So that's a delay. When you don't want to have magnetic energizing and de-energizing vocabulary because you don't have any relays, you still have a timer, and the timer does the same thing. The timing starts when the power is removed. The output is deactivated after a specific time. So that's what's going on with that symbol. There's a program element, and we're finally getting to that point in the presentation. The PLC has that as a program element. Remember, here is our registers that are inside the PLC, and there is where this program element happens to be. Right? It's register 5304-4 and 5, but the count is sticking its head into the game. There's register 5301, 5302, 5303, 5304. So what's the problem? Problem is, a lot of times you don't think about it, but you say this is 1, 2, 3, 4, and 5. This is not bit location 5 because you're still in base 8. So this is location 0, 1, 2, 3, and 4. Don't let your students get caught in that trap and avoid it yourself. All right, there is an on-time delay, there's an off-time delay programming element. So we're finally ready to get back to the address assignments. Right, there are the locations, and there are the players that finally are important to the outside world, the relay mixing, and the motor that makes the relay fill and then starts the mixing. And finally, the program. And we can stare at this and work on this, right? The program does not, a big mistake you can make is just try to rewrite this. For a starter, this symbol right here was the intent, but it wasn't done with a delay, right? It was done with a delay off. It was done with the delay on, right? So that you could accomplish what you wanted. The start button and the seal in concept are from the fact that you managed to get over here to the energize the motor. There's the addresses for what's going on. Notice there's also an internal contact called FR1 that keeps information from going this way when the field is not done. We can talk about this when you have specific questions in a minute. So this is what's going on. All right. So you have to have documentation in the professional world to build a program. So don't let your students just invent one. Give them documentation. If you have a schematic ladder diagram, what do you ask them to do? Verify they understand the idea, and that's what's supposed to be done. Many of these diagrams look the same, so you could pull the wrong one off the shelf. Study and understand every icon. Right? Remember that you have to keep going in an ordered event. Otherwise, you will have a trip. Okay, so what's the message here? The message is you spend a lot of time with your students working on the vocabulary and the continuity concept, and you make them always use this vocabulary all the time. Even though in your laboratory, if you're an instructor here or a faculty member, you may have any one of the ones I showed you, but in real life, that's what you need to do. All right, so that's what's going on with that. I do have to acknowledge an important idea here. And that's the animations. And the one thing I wanted the animations to do was work, and they aren't doing that. So that's life. And let's see if it works now. Yep. I have to give credit to the people who are actually triggered any humor that you got out of my drawings. They were my drawings, but it was their humor. And I think it's time for me to take a little nap. And I hope this material was helpful. And I'm certainly up for some questions and input. And I don't know how to let you have control of this stuff, whoever's out there, but go ahead.
If anyone has a question, can unmute and ask or write in a chat. In addition to whoever is typing something related to music, we don't know who is.
I have a question. How many people who are teaching have to deal with more than one type of PLC? I guess you couldn't hear me there. Well, that's too bad. I have to type something somehow. Oh, I could have done
We
that.
can hear you, Richard.
Okay, so is anybody responding to that they have more than one type of PLC in their laboratories?
Yeah, if you want to respond, you can just take yourself off mute, I believe. It's in the bottom left-hand corner.
Okay, if you only have one type of controller, that's the way it is, but make them at least simulate and tell them it's a different type of controller. Industry 4.0 equipment, as it comes into the real world, will have different types of controllers. And the Japanese controllers will be the prime choice. And my observation so far.
All right, so if there aren't any questions, it looks like everybody's muted. So if there are questions, I'll pause for 30 seconds here to give you a chance to get off mute. Okay, well, hey, thanks again, Dr. Gilbert. Really appreciate your presentation on PLCs. And for those of you that aren't aware, Flate produces many webinars, certainly over the last few years. And here's a list of some of them. You can get to them by going to the web address below. And like we mentioned, if there's some other subjects that you're interested in, please let us know. I know AI seems to be one that's popping up a lot. So any other subjects that you might think are important to you or your students, let us know, and we'll try to find a professional, someone with some experience to do the webinar for us. But unless there's other questions, thank you for attending, and thanks again, Dr. Gilbert, and we will talk to you all soon.